Hello everyone, welcome to today's session. In the previous video, we said that robots need to sense the environment and also need to be able to apply forces and torques, and they need actuators. Today, we're gonna talk about specifically action and perception element in robots. Why do robots need sensing? And well, this picture kind of explains it. The robots need to know where they are. They have to be aware of their surroundings as well in order to avoid accidents. And also, it's essential for them to do their tasks. So, they need to know generally two types of information. They need to know about the state of themselves in the real world, and also they need to know about the world around them. If the robot needs to pick an object, it should know where the object is. If there is an obstacle in front of the object, it should know where the obstacle is in order to avoid it. And this type of information is itself can be categorized into two groups. And we have similar concept in images and image processing as well. We said there are two types of information in an image: semantic information and metric information. It's the same for the robots. The robot can have require some semantic information. For instance, example of the pick and place robot. If it needs to pick an object, for instance, a glass between several other objects, it requires to know what that object is, what are the objects around them, and go and specifically pick up that glass. So that is semantic information about the nature of an object. It also requires metric information, for instance, how far the object is, how far it is from the other objects. And when you think of it, there are quite a lot of different types of information that we can get from sensors. If we're looking from getting a distance, we can have different sensors. For instance, camera is a good sensor to measuring distance from an object or distance between various objects. Another ways to measure distance could be, for instance, based on the sound that an object emits or the smell. Some robots require to have a sense of contact, and contact can have different definitions. For instance, tasting, feeling pressure or temperature. Consider a robot that needs to pick up a soft object. It would require to feel the pressure that it applies to an object in order to not really compress it and destroy the object. That's a specific type of information that it can get through a sensor. Another type of information is the things that the robot needs to know about its own state. For instance, it needs to know where it is, what are the angles of its joints, or where is the position of its end effector. And some robots need to know if they are damaged. For instance, we don't want to have a damaged robot working inside a factory line. It could break and cause an accident. So we need sensors to measure the state of the robot to see if it's healthy or damaged. Based on all of these, we can categorize sensors in three different types. First type is exteroception. An exteroception sensor gets information from an external source. It gives the robot information about its surrounding. For instance, a car that has a camera. Usually, most of the cars these days have a back camera or a front camera that can detect the objects. If you're gonna hit an object in the back, you can see it through the camera. This is an example of exteroception sensor, a sensor that gives the driver or the car itself, if it's self-driving, information about the surroundings, something external. We have proprioception. Proprioception sensors are the sensors that give information about the robot itself, about the states of the robot. An example is an encoder. An encoder is a device that can measure the angular position of a joint. It has a shaft that if you connect it to a rotating joint, let's say this, it will tell you what is the angle of that joint. What is this angle between the two links? This is an information about the robot itself. Therefore, it's a proprioception. We have exproprioception as well. This is a type of sensor that is a combination of the first two categories. It gives an information about the robot and the way it's interacting with its surrounding. An example is a collision detection sensor, an object detector like this. Again, in some cars, they have a rear view camera and also they have an object detector. If you are colliding into an object, it beeps and informs the driver. If it's a self-driving car, it informs the central processing unit of the car that there is an object out there and it's colliding with you. So it gives an information about the robot interacting with the environment. Now, some terminologies that I wanted to talk about and introduce you to those. Uh, a robot, basically, we briefly discussed it in the previous video, is composed of links. Links are rigid parts of the robot that are connected with several joints. So every robot is made of links and joints. And every joint is usually actuated and it has a motor connected to it. And for instance, these joints are all rotary, they can rotate. They have a motor here that rotates these joints, motor here. And the motor doesn't have to be essentially at the joint, it could be far from the joint and then has a transmission system that applies force or torque to the joint, for instance, using a timing belt and a pulley. And also, a robot is usually equipped with something that we call an effector. Like here it has a gripper or a grasper. Effector is a tool that the robot uses to do a task. It could be itself robotic, like in this example where the grasper is a robot itself, or it could be just a manual tool. It could be like uh, welding equipment to weld cars. So the effector and actuators are something that we talk about a lot in robotics. Effector means something, the tool that the robot uses, and actuators are used to move the joints. There are various types of actuators. Actuators basically transform an energy source into a motion. We have pneumatic actuators where they use the power of high pressure uh, air. Like this one, this is a pneumatic actuator. If you put high pressure air inside of this actuator, it can move back and forth and it can be used to move a robot arm. Another type of actuator is hydraulic actuator, where they use high pressure liquid or fluid. It could be oil or water. The same concept as pneumatic actuators, but they use fluid. And a high pressure fluid can be pumped into this actuator to move it back and forth and then used in a robot. The most common type are electric actuators like DC or AC motors. You see electric actuators more in robots. Hydraulic and pneumatic actuators are used for robots that need to do a very demanding task, something that requires a lot of power. For instance, in construction robots or in agriculture robots, they use pneumatic or hydraulic actuators, but normal robots use electric actuators. There are other types of actuators I didn't talk about, like piezoelectric actuators, or in the old times they used steam engines where high pressure vapor used to actuate something. But these three are the most common types. Another way to categorize actuators is by the motion they offer. They could move a joint linearly or they could be rotary. And as I said, a robot is composed of several links and joints that are actuated by motors. And it could be again rotary or linear. For instance, this very simple robot that we see here, schematic of the robot, it's used to pick an object and move it. It has one rotary joint here actuated with a motor and two linear joints that we sometimes call prismatic joint, and the rotary joints are sometimes called revolute joints. Revolute joints move a joint by an angle and linear joints move it by a specific distance. So a robot can have any of these joints, prismatic, linear, or rotary and revolute. And finally, I want to talk about a concept called degree of freedom, which is used to quantify robots. And what does degree of freedom mean? Degree of freedom means how many different types of motion can an object have in 3D space. For instance, if you look at this piece of brick in 3D space, how many different types of motion can it have if you want to pick it and move it? You can move it up and down, left and right, back and forth in 3D space, and you can also rotate it around three axes. So a simple object in 3D space usually has 6 degrees of freedom. You have 3 linear motions and 3 rotary motions for an object. And you can also constrain an object and say, for instance, if this brick has to stay on the floor and we're not allowed to lift it up, then how many degrees of freedom does it have? In that case, it will only have 3 degrees of freedom. It can move back and forth, it can go left and right, and it can rotate it in place. Then it has 3 degrees of freedom. Now, degrees of freedom is a bit abstract concept. It really depends on what do you want to define it for. A degree of freedom can be defined for a task or it can be defined for a robot. For instance, in the previous image, I defined it for a task of picking a brick and moving it in 3D space. Then we had 6 degrees of freedom. Another example is if you want to just lift an object, if you want to just lift the brick up and down, then you have only 1 degree of freedom. So degree of freedom can be defined for a task. A degree of freedom can also be defined for a robot. That means how many different types of motion can the robot have, and basically how many different joints does it have. For instance, if you look at this robot, it has a joint that can rotate here, has another joint, revolute or rotary joint here, has a joint with a motor here, and it can move linearly here. So we say it has 4 degrees of freedom. So degree of freedom for robot is how many different types of motion can it have as joints. And finally, based on this, we can define how to use a robot for a specific task. Assume a robot that has 4 degrees of freedom wants to move an object in 3D space. It requires 6 degrees of freedom. And for that case, we say the robot is under actuated. It does not have enough degrees of freedom to do that task. if the degrees of freedom of the robot are less than the degree of freedom required to do a task. Exact opposite case, if the robot has more degrees of freedom than doing a task, we call this a redundant robot. Consider this robot, if it wants to just pick an object up and down, the task has 1 degree of freedom going up and down, but the robot has 4 degrees of freedom. This is a case the robot is redundant. It's easy to understand that a redundant robot is useful for doing task. It's easier to do a task when a robot is redundant. You have more options in terms of controlling the robot. However, when the robot is underactuated, you're limited, and an underactuated robot usually cannot do everything that you want to do. It's limited in its options. And as I said, a degree of freedom is a bit of an abstract concept, and you got to look at it based on the task or a robot. A degree of freedom is even defined for any mechanism. For instance, if you look at your arm, let's see how many degrees of freedom does your arm have. Elbow here has a joint that you can bend it. It has 1 degree of freedom at the elbow, right? Elbow can also a bit twist. So 2 degrees of freedom here. Shoulder can do up and down, 1 degree of freedom. You can go left and right, 2nd degree of freedom. Also, you can twist it a bit, 3 degree of freedom. So far, 5. How about the wrist? Wrist has 1 degree of freedom going back and forth, 2nd degree of freedom going left and right, and you can also twist it a bit. So 3, 2, 3. If you consider your fingers, then your fingers have add more degree of freedom. So if you want to pick an object and move it in 3D, you have more degrees of freedom than required to do that task, which is 6 of tasks. Thus, your arm is kind of a redundant robot. And as I said, redundant robots are more useful.